internal load of a cross section along a steel shaft of a ship. Okay, so I'm going to get the image of the steel shaft. Okay, so this is the steel shaft of the ship that you can see. Okay, and it has a torque of 2,300 foot-pound. So this is a torque. All right, and it has a bending moment of 1,500. Okay, so this is a bending moment that you can see. And it's also going through, it has a axial load. Okay, so this is an axial load, right? This is an axial load. And then if the U point for tension and shear are 100 KSI and 50 KSI, determine the required diameter of the shaft using the maximum shear stress theory. Okay, so if you look at this problem sum, right, and if you were to refer to 2P04, right, we are combining 3 chapters of 2P04 to solve one engineering problem. Okay, this is the real world. Okay, this is 3D. Okay, this is 3D stuff. This is the real world. Okay, what you'll see are problems like this. Okay, there won't be any isolated problems. There are problems where you have a combined axial loading, torque, and what? Bending moment. Okay, so first of all, like whatever things we do, okay, we need to have a transformation. Okay, so we're going to have a transformation. So any problem set that you see, you're going to draw a transformation first. Okay. So the purpose of our calculation is to design what's the minimum diameter required, or in the near future, if the structure were to fail, right, and you'll be under prosecuted, okay, another engineer has to be capable of looking at your calculation to say, hey, the failure of this structure is not his calculation. Rather, the failure of the structure is based on the manufacturing process, and we have to look for Eugene also. Okay, so both of them are my fault. That's why I take teaching this course very, very seriously. Okay, so the first thing that we are going to do, okay, for a problem like this is we have to how to identify we have to find how to identify the types of loading. Okay, so what do I mean by how to identify the types of loading? So what is what we call axial load? Okay, what is due to shear force? What is due to a torque? And what is due to a bending moment? Right. I'll give you a typical example. Okay. Can someone give me the formula for torque, please? Anyone?
Force times radius.
Well done. Torque is equal to force times radius. Right? And then what is a bending moment? Anyone? What is bending moment equal to, please? Hello?
The integral of all the shear force moments.
No, don't go there yet. Okay. What is a bending moment?
Is it not like force times length, perhaps?
Force times perpendicular. Okay, distance, not any other distance. So if you look at both of them, they are very similar, yes or no? The radius is also the perpendicular distance of the force. Am I right or wrong? Right?
You're right.
Right? It's like, hey, what is a moment and what is a bending moment and what is a torque now? You can identify this very easily, okay? So to identify is based on deformation. Of the centroid. Okay? Of the centroid. So let me elaborate this. Okay? For this problem set, right? For this problem set, I'm so excited now. I cannot sit down. Okay? For this problem set, right? They tell you what's a torque. Okay? What's the bending moment, right? That's the problem where we train you as an engineer. When we train you as an engineer, we gave you too much information. Okay? The reality is you in the real world, you just go to the engine room of the ship and you have to stand down there. What is generating the torque and what is generating the bending moment? I want you guys to be able to identify that. If you can't identify that in this course, okay, I fail. Okay, so this part of the course is going to be taught in week number 8. Okay, week number 8, I'm going to teach you to identify what's a torque on bending moment. And we are going to do 3D stress analysis, not 2D, not 1D, but what? 3D, okay? We are not going to do 4D because I don't know how to calculate the stress of a shadow, okay? But anyway, stress of the shadow, right? So coming back to over here, okay? So if you look at a deformation, okay? So if we look at bending moment, okay, we look at a bending moment. Right? So if we look at the bending moment, if we draw the deformation of the bending moment, right? So the deformation, so if I were to look at this shaft, okay, I'm going to mimic the transformation over there, right? So this is my Y, and this is my X. That is why it's so important to draw the transformation. Then we know what we are looking at, okay? So if we draw that, so we look at the shaft doing here. So this is the shaft, right? This is the shaft. And the shaft is having a rotation in this direction. So this is our moment about the z-axis and is equal to 1,500 pound-feet. Okay, so this 1,500 pound-feet, the deformation pattern, how it looks like, the deformation will look this way, right? And the pink is the deformation pattern. So if your deformation pattern is a smiling face, okay, is a smiling face or a sad face, then it's due to what? Bending what? Bending moment. Okay. Now, if we view this with the same view, right? If we view the structure again in the same way, right? And now we have a torque going this way. So this is the torque. And it's equal to 2,300 pound-feet. Now, this line I've drawn is known as a centroid. Okay, this line I've drawn, that is also the centroid. Can someone tell me, due to the torque? Oh,
Professor, can you go down?
I know, my sorry. Okay, I need to like really calm down. I do apologize. Okay, so I've drawn the same thing, right? Now the torque is going about 2,300 pound-feet. Can someone tell me how will the centroid deform due to the torque? Anyone? How will the centroid deform?
Happy face?
No, the centroid will still be on the straight line. The centroid, I'm going to use a ticker. The centroid will still be here.
Towards us?
No, the centroid will still be a straight line. It will not become a sad face or a smiling face due to the torque. Okay, so that's how, by looking at deformation, you can identify what is a torque and what is a what? Bending moment. Okay, so I will go into more detail on week 8 down here. Okay, so week 8, we'll go into more detail on how to identify a bending moment, torque, and shear stress, okay, or shear force. You guys have done shear force before in 2P04 in bending moment and shear force diagram. I'm not so worried. So in this context, what we know is we know that we have a load known as Px, okay, and Px is equal to minus 2,500 pounds, okay, and this is caused by axial loading. Okay, this is caused by the axial loading. So that is why it's important to able to identify the load. So now from here, you know that you have a torque in the x direction that's equal to 2,300 pound-feet. Okay, and you have to transfer this to 2,300 times 12 and multiply by 12 because you want it to be in inches. So this will be equal to 27,600 pound inch. Okay, and then finally we know that we have a moment in the z direction, and then from here you have 1,500 pound-feet. Again, you have to transfer into inches, okay, or pound inch. So this is equal to 18,000 pound inch. Okay, so from here we have identified our loadings. Okay, next, from this loading we are going to calculate our stresses. Okay, so from the loading we're going to calculate our stresses. So I'm going to go to the next. Okay, so we are going to, from here we are going to calculate the stress state. Okay, we're going to calculate the stress state, right? So the stress state. Wait, can the quiz be open for the whole day? We'll talk about the quiz later. Okay, so can we calculate the stress state? Okay, so stress x is equal to px over a. Okay, so stress x means the stress in the x direction. Okay, let me also copy the diagram so you can see better. Okay, so you can see. So the stress x, the force x is in the stress x in the x direction. So we are calculating stresses in this direction. Okay, so this is my x again, and this is my y, and then following down here, this is my z. Okay, so it's px over a. Now don't worry whether it's plus or minus first. Okay, we can look. I'm going to teach you by looking at the deformation. We know whether is it tension or in compression. Okay, then you have plus over here, right? So moment in y divided by Iyy multiplied by z. Okay, then plus by moment in the z-axis divided by second moment of area in the z-axis multiplied by y. Okay, so over here, the px over here, this is known as our axial load. Okay, due to the axial loading, right? And then the next two over here, right? You guys have seen this before. I know Dr. Koshi probably have done this in the last 3 weeks of your lecture. Okay, then over here you get to see your bending moment. Okay, right? So this topic over here, and we are also going to cover sandwich material for eccentric loading. So this will be done in week 1 and 2. Okay, so after our introduction, we'll be starting to do bending. Okay, again, the bending, we are going to combine sandwich material with axial and bending moment. Okay, not just so in 2P, I believe you guys were just taught sandwich material under bending. Okay, and just under pure bending. How do you treat axial loading? Okay, which has been taught to you guys. Then the next one, so this is the normal stress. And then you come to know about the shearing stress. So shear stress, there are two components. Okay, shear stress, there are two different types of shear stress. The shear stress one, which is really familiar to you guys, you have TR over J, where J is the second polar moment of area, right? The next one